Okay, so it looks like I've got a few people here today. Two people who are new.
A little louder, please.
Two people who are new today. And I was hoping, because this class, there wasn't that many people here last week. I was hoping even less would come this week, okay? Because what happened was I didn't do what I wanted to do to prepare for this class. I prepared for a different class, astronomy class. So what happened is there was a flood in my apartment. Not a biggie, my fault. So I ended up playing plumber in my own bathtub and spent the better part of last night screwing around with my bathtub. And basically didn't have time to do everything that I wanted to do for you today. So, but on the other hand, I retired in 2012. It's 2018. So, no, it's, 2000, I'm sorry, wrong. I retired in 2006. It's been 12 years since I retired. In those 12 years, I have not earned a single penny. Okay? But on the 30th of this month, the Amateur Astronomy Association of New York City has decided that I should give a lecture, and they're going to pay me money. Okay? So I'll become an honest.
I signed up for your class.
You did? The one in January 30th?
Mm-hmm.
You did. So we have a customer.
Where is it?
It's someplace.
35th and 8th.
35th and 8th. There you go. How do you know about this?
I joined the club a couple of weeks ago.
Really?
So I signed up for their classes, and you're giving them one on that night.
But how did you find out about this club?
When I looked up your bio from teaching that class, I saw that you had this.
Okay, so I advertised I essentially I'm giving a course, okay, and on the course my bio mentions this class, and she came here from that. So this is called marketing, okay? So good. But the thing is, what I did. So what I'm going to give the lecture on is not my usual stuff that I do here, which is like anything and everything. I have a specific topic. And the topic is astronomy simulations. So what people are going to come to see is astronomy simulations, and I'm there to tell them what you can do by looking down on your computer rather than looking up in the sky, because I don't look up in the sky, but I'm very good at looking down on a computer, so it makes sense for me to give that kind of lecture. The problem is, it doesn't make that kind of sense to give that kind of lecture to you people, because I assume the people who are going to that class, and I'm assuming this, are people who are interested in getting their fingers dirty, touching the keyboard and repeating the simulations that I'm going to show you, some of which today. But from my knowledge of you guys, there's only one person or none person in this class who will actually, after this class, turn around and go to tinyurl.com/Laird-astronomy-simulations. Type that onto the URL of their computer, get this page on their screen, and then proceed to use some of the hints that are on this screen, which is what I'm going to be going through today, to say, oh, Laird talked about it, it's right on the screen, I can do that. There's nobody in this class who's going to do that.
You're right.
Okay? Right? So you, except one person.
I may.
You may, because we have two.
Well, my computer's not working, so.
Wait, you see, and here's the worst part. If your computer's really old, which is true for mine, it isn't going to work anyway, generally, because you need a faster graphics card. If your computer's 10 years old, it may or may not be able to struggle along. Fact is, mine couldn't. So if anybody who knows about my computer knows that this is not the one I always bring. This one's 10 years newer. I bought it by accident because I thought my old one was going to die, but it didn't, so I have this one. So this is great. This is the one I actually need to do this today. And you can use some older computers as well, but
No, mine is new, but it's just I don't know how to use it.
you don't know how to use it. It's new? Okay, you give me a haircut, I'll show you how to use your computer.
Sounds like a good deal.
It sounds like a good deal.
Carter.
Let me tell you what I can do. Let's see what this. First of all, let's see what the list of these things is. Okay, there is, and basically there are notes to myself in here. And by the time I do this class in 2 weeks, I'll get rid of these notes so it won't look like this exactly. But basically the basic form is here. There's a piece of software called Universe Sandbox, which I've never used in this class, and it's cool, and we're going to do some of that, and we're going to do some cool stuff, including a video of Planet 9, or at least showing you the orbit of Planet 9, even though we haven't found one yet. I got a simulation. Okay, I got I got some of the furthest planets out there in the solar system as well. They're there in the simulation. In Starry Nights, I have a nice simulation of the universe. Okay, the local universe called Tully. That's what over here, and I have a flyby of the moon and. Some cool stuff with Mars. In part of you, this is what I'm trying to do today. Okay. In part of you, I've used part of you a lot in this class. I could literally spend the entire class just doing part of you, and I would explain the universe to you in gory detail and basically these are things I'm going to do anyway in class. Normally, I'm going to use part of you to show you what the universe really is. Because I've been teaching this class now for 12 years, 11 years. In the last 2 years, I haven't gotten out of the solar system. Literally. Anybody who's been in this class knows we hardly talked about stars, galaxies never mentioned, the universe not at all. So part of you is useful for talking about that. We're going to talk a little bit of part of you tonight. Uniview Theater is cool. It was given to me by the Museum of Natural History. I spoke to one of the people who worked the planetarium, and he gave me the software that the Museum of Natural History uses. So I'm going to show you a little bit of that. But if you were trying to follow along in your workbooks, you can't, because that one's mine and you can't have it because he gave it to me and I can't give it to you. Then there's NASA's eyes. Let's see. There's NASA's eyes, which is something that NASA does. It's cute. Tells you about all the missions it's been on. We can do some of that. Probably not today. Stellarium is a very cool place to go, but only if you happen to be an amateur astronomer. Because if you're an amateur astronomer, you really want to see what the sky looks like, so you can use that to point your telescope. So we're not going to do Stellarium today. Exoplanets might be fun. We're not going to do it today, probably. Solar System Visualizer, just one of those things. Open space is cool because you can, with open space. This is really nice. It's 10 years, 12 years since they started making this stuff available for the public. The Uniview that I told you can't have is being made again for the general public, and everybody can have it. So open space is the thing that is the best thing going, but it's somewhat broken because they're building it. So I'll show you a little bit of that today too. Obviously we could spend hours doing this. And then what else? Then there's Google Earth, which I can show you. Want to take a look at Earth, Mars, the Moon? Google Earth for that. Celestia is good for stuff. So there's a lot of simulations that we can do, and what I'm going to do is just a couple of those today. Starting with, let's see, what's at the top here? Okay, Universe Sandbox. Okay. Universe Sandbox is fun. Oh, what do I have to do with it? Anything small? Okay. But most of these are not web-based in the sense of that you don't need a strong internet connection, because what you do is you download the stuff. It's free generally. This one's $25, and then once it's installed, you just tell it to go. Now, the whole point of this here is I'm going to be touching on stuff. It isn't really important that I do this, what I just told you about, okay? We can skip everything. If you have a question, okay, that relates to anything you see here, let's stop the train, everybody get off, and we'll talk about that, okay? But in the meantime, there are lots of, because instead of like talking about one topic, like I always do, I'm talking about every topic. So there'll be this topic and this topic and that topic, and there's no reason not to stop at a topic and say, hey, wait, let's talk about that. So I like this one. This is one of the, first of all, this one comes with sound. It's very nice. Turn the screen here. Okay, so I like this one because you really get a sense of our solar system in the context of the Milky Way, and you get to see all these different objects doing their thing, and in the right way. The ones around the sun cutting in close are going fast, like Mercury, Venus, and the Earth. The ones that are further out, Jupiter is moving much slower, and some things that aren't planets, like Ceres, which is an asteroid, or Pallas, which is another asteroid. You see them in the asteroid, but you see Mars, and there's Vesta, another asteroid. You see little asteroids without names floating around, and other small moons. But I pull out and it's nice. There's Neptune. Somebody asked me how fast Neptune was going, or Pluto. You see, Neptune's not moving fast at all. It takes hundreds of years to go around the sun. You see the asteroid belt in there. But there are lots of other things running around loose here. A lot of the things you see are not stars. Let me see if I can emphasize that in some way. No, I can't. Okay. As you pull out even further, we get other planets. Haumea is a planet, but not one of yours, but one of the dwarf planets, and Quoar, and Orcus, and Maki Maki, other planets, dwarf planets. And two of my favorites, Eris, which is bigger than Pluto, Sedna, which goes out forever, out to the distant solar system. Now, this is the simulation that starts Universe Sandbox. But Universe Sandbox, the word sandbox means that you can play in it. So people are encouraged to come and play. And what that means is they're encouraged to come and build something that, using the laws of physics and gravity, build something in the universe. So some people come and they build all sorts of extraordinary, crazy things. We're going to skip those. We're going to skip the ones that people build that aren't extraordinary and crazy. They're just real. So among the really nice things is this one, for example. This one shows you the most distant solar system object. So as I pull out, you can see the inner solar system is very small, yet that object goes out almost a light year, and yet it's still part of our solar system. There's another I'm doing another simulation. This one is called the Goblin, and the Goblin, it says TG. The name of this thing is 2015 TG 387. TG is how it got its name, the Goblin, TG. It was discovered around Halloween, and so it still carries that name, the Goblin. And it, among others, is very far out. There in the solar system. I think it's a little too loud. Okay, so those are two of the simulations I like in this thing, but there are others. Okay, you all have heard about an interstellar object with a hyperbolic trajectory. This is a visitor from another star. This is a visitor from another star. We only saw it when it was around here. We saw it for the first time when it was around here. We didn't see it come in from here. We didn't see it come in from here, and we only saw it as it's leaving. Never to be seen again. It's very sad. There are ways that we could catch that sucker if we spent billions and billions of dollars. We could mount a program, because it's going to take years to leave the solar system. In the meantime, we could build rockets to go there and check it out. It wouldn't be worth it, although it would be, because we literally would be sampling something that was made at another star. But we're not going to do that. But it's interesting to note that it can be done. It just costs like $100 billion. Yes?
You explain, what was the difference between parabolic and hyperbolic?
Parabolic is...
2x plus 3y equals...
Yeah, no. This is a cone, okay? It's a cone. And an ellipse is a section taken through this cone that cuts off like that, an ellipse. That plane cutting through that conic section produces an ellipse. If you take that same plane and you have it vertical like that, it will cut off a conic section that looks like that on the side, and that's a perfect parabola as long as this thing's perfectly down. If you have this thing come in at an angle like that, the conic section that it cuts off is a hyperbola. Okay? All right? Does that mean anything to you, what I just said?
Well, one of them is where you hit a baseball
Right.
at 45 degrees, probably goes the farthest.
Right. The baseball will go in a parabola. Anything you throw up on the Earth will do the parabolic thing. Although in truth it's really doing the elliptical thing. Okay? But it's very close to the parabolic thing. Okay? But the parabola is only when you hit anything that's going around the Earth is an ellipse. Okay? Anything that leaves the Earth forever, That's a hyperbola. Anything that goes almost leaves the Earth forever, but then falls back down again. That one special case, that's the parabola. Okay, the parabola is a special case of an ellipse merging into a hyperbola. It's the one that's singly in between. It's known as the one with an eccentricity of 1. All the hyperbola has an eccentricity that's greater than 1, ellipse eccentricity that is less than 1. Parabola, exactly 1. That's why it's unique. Okay. Did anybody else get that one?
Is the definition of our solar system, is that defined by the range of the sun's gravity, that everything is orbiting?
No.
How do they know what the edge is?
What is the edge of the solar system? The solar system, you could say, has no edge. And then you'd say, well, okay, that doesn't sound right, it has to be an edge. But of course it doesn't have an edge. If the solar system was isolated in the universe, then the sun's gravity would pervade the entire universe, as it does. The sun's gravity does pervade the entire universe. There's no end to the gravity of the sun. It gets weaker, but it doesn't end. So what makes the end? The end is when another star's gravity is stronger than the gravity of our sun. So when the competing gravities finally reach an equilibrium, that spot between the two places, that's the end of our solar system, gravitationally speaking.
So when they say this is the furthest object out in our solar system, it's the last object they can find that's captured by, that's orbiting, that's captured by the sun?
You're talking about the further? Are we talking about that thing?
Yeah,
Uma,
so this is the furthest object in our solar system.
it is that object. There came from outside of our solar system, from another star.
Not the hyperbolic.
Not the hyperbolic.
No,
What are you
before
talking about?
that, you showed, somebody had shown the furthest object out in our solar system.
Oh yes, I showed you a planet which was the furthest object out in the solar system.
How is that the furthest object?
It's the furthest object. The furthest object we can see that we have an orbit for. We
So it's
know.
orbiting.
We know there are further objects than that. We know it. It's just that that's the one that we actually have seen
So the definition is that it's orbiting.
orbiting.
Okay.
Anything that's orbiting our solar system is in fact in our solar system. And although that object that we saw, which was called the Goblin or Far Out, whatever those things are that are far out and that I showed you, there are things that are much further out that still belong to our solar system. We haven't seen them, but we know they're there. And the reason we know they're there is because every now and then one of those things comes in to greet us. We call those things comets. Sometimes a comet which has never before seen in the history of mankind comes to greet us in our inner solar system. We calculate the orbit of the thing, and we realize that it comes from incredibly far away, maybe almost a light year away, but it's in fact part of our solar system. It's been dropping down for millions of years, and finally in the last few hundred, and then tens, and then 1 year, it finally makes its way to the inner solar system where we can take a picture of it. And so we know there's trillions of those things. The ones that are interesting that I showed you are in fact the ones that we actually have an orbit for, and we know it's in and out and in and out and in and out, and its orbit is not millions of years, but thousands of years. So it's close in, but still the furthest that we see.
So if it comes back,
And it will come
it's not
back.
hyperbolic.
It's not hyperbolic.
It's part of our solar system.
It's part of
Even
the solar
though it
system.
might leave the solar system.
May have an orbit of 40,000 years, but it will be back. Those comets have orbits that are like 1,000,000 years, and they come back, usually. Yes?
We define the solar system as having an end, the last thing that is orbiting the sun. it has to stop somewhere and things are orbiting something else or just randomly moving. Wouldn't that be the edge, the end of the solar
The edge of the solar system. Here's what it feels like at the edge of the solar system. Obviously, if you are one of those objects that is the edge of the solar system, you look around you, you see nobody near you, because it's very vast out there. And although there are trillions of your neighbors, you can't see any of them because they're small and they're far away from you. But you are at the edge of the solar system, let's say, okay? And let's say you've got a fictional gravity meter, okay? There's no such thing, by the way, as a gravity meter. You can't hold up anything in outer space like they do on Star Trek and go, I feel there's gravity there. You literally can't do it. You know why? Because you are the gravity meter. If there's gravity there, you're being pulled towards it. And the gravity meter is being pulled towards it. So the two of you, the gravity meter and yourself, are being pulled towards that object. And so the gravity meter reaches a zero because you're moving along with whatever is pulling the gravity meter. No gravity meter. Nevertheless, we could say there is gravity out there. And the way one could see it is I'm over here. I'm not on that thing. So I'm looking at you and I can see what's happening to you. See, you can't measure your gravity, but I can. Because I can see if you're being pulled that way, you're going that way, you're being pulled that way, you're going that way. So I'm watching you, okay? And I see you were in an orbit that was going around the solar system. And it's a million-year orbit, but it's still part of our solar system. Oh yes, you're part of our solar system. But there are stars that are passing by our solar system all the time, okay? These things pass by on the order of tens of thousands to hundreds of thousands of years. But astronomically speaking, just the blink of an eye. There is a star called Barnards Star that is headed our way, at full speed, faster than any star in the sky. It moves so fast that from the time you were born to the time you die, that star has moved in the sky, literally. You can see it move. You can, if you had really good instruments, you could see it move from Wednesday to Thursday, if you had the really good instrument. That star is moving past in the sky. In 40,000 years, that star will be closer to our Earth than the nearest star. It will be the nearest star. It's called Barnards Star. When that star gets close to the Earth, maybe that little piece of a fleck of stuff, that schmutz out there all the way at the edge of our solar system, notices that maybe it would like to follow that star around the universe instead of following our star around the universe. So it switches allegiances and it starts to follow that star. That's the edge of the solar system. When an object is so far away that it can be pulled by a nearby star and change where it, in fact, follows for the rest of its duration. That's the edge of the solar system. But right now we call it 1 light year, more or less, in terms of gravity, because we think that we think that the rest of the universe, although we're not, one single star can't pull us away because the nearest star is 4 light years away. But there's billions of stars out there. And even though they're far away, they contribute. So we think, okay, at the edge of the solar system, 1 light year, those billions of stars have something to say about the fate of anything that's laying out there. So arbitrarily we say 1 light year is the edge of the solar system. That's gravitational edge. There's another edge, which is the edge that you see if you're talking about how strong our sun is in terms of spewing forth its solar wind into the interstellar medium. The interstellar medium has its own gas. It's very, very undense. So undense that there's a molecule here, and then there's a molecule here, and then there's another molecule here. And it's really nothing out there, but there are molecules. To grab a handful of space, you'll grab a handful of molecules. So that out there in interstellar space is where the molecules coming from the sun meet the molecules that sit in interstellar space, and the ones from the sun, which are moving at a fast rate, hit the ones from interstellar space, which are just dawdling along. these hit these, and then suddenly they merge. And suddenly the sun doesn't get to blow past into interstellar space beyond a certain distance. That's the edge of the solar system as far as the sun is concerned, as far as its solar wind influence. We call that the heliosphere, the heliopause. And the heliopause is really where spacecraft have come and gone through. Two spacecraft have already traveled past the heliopause and into interstellar space, although they're nothing like a light year away. They're less than a light month away from us. Yes?
So does that mean that the only thing that gets past the solar system
What is over
would
there?
be the light from the sun?
Does that mean that the only thing that gets past the solar system is the light from the sun?
It's past the solar system. You can see it from outside the solar system.
Okay. I like Barbara. She asks great questions. Yes, Barbara. That is the only thing that can get past the solar system is the light from the sun. That is true. Except, as long as you asked, for the times, if you're talking about, what kind of light are you talking about? Are you talking about visible light? If you're talking about visible light, the problem about visible light is that visible light gets stopped by interstellar dust. So interstellar dust, although there isn't much of it, when you pile up light years and light years and light years and thousands of light years of interstellar dust between you and me, you're the star, then there's a cloud, the class is a cloud of dust, and then there's me, I can't see you through the dust. So, have you ever noticed the Milky Way? That's your cloud of dust. You don't see stars on the other side of the Milky Way because the dust stops your vision. You cannot see the other side of the Milky Way. That Milky Way there, you see this black cloud there? That's interstellar dust right there. You can't see the stars behind it. So, but if you were an animal that saw in the infrared, then infrared is a longer wavelength, and the dust is small. See, visible light is this small, and the dust stops it. But infrared light is bigger, the wavelength, and it can get past the dust. So if your eyes were infrared, you could see through the cloud of the Milky Way and see into it and further out. Eventually it stops anyway, but they're building a telescope that's designed to do just that. It's called the James Webb. It's billions of dollars in cost overruns. And the whole idea is it can see deeper into space because it's bigger. It's a bigger telescope looking at larger wavelengths, so it has to be bigger. And it will be able to see where no man has seen before. This will be cool. You ask good questions.
How long will that take to
How long will it take to build that telescope?
Yeah.
Billion years.
I have a friend who was getting a PhD at the same time I was, and we were both in the fifth year of our PhD studies. It took us each 7 years to do it. I asked, and he's a very funny guy. I said, Bob, how many years till you finish your PhD? And he said, N-5. N-5. Because he and I were both, engineers, mathematicians. N is undefined. -5 was well defined. We had been at it 5 years. So, in terms of the James Webb Telescope, when it will be done, N-7. Okay, it's about 7 years delayed. They tell you that it's going to be in a year or two. They have said that for 7 years.
I just wonder if I'll be around. When
I wonder if I'll be around. Good questions. Thank you for keeping me from doing this. In the class that I'm going to do, I expect nobody will ask me questions like this, because everybody in the class that I'm going to do, everybody's going to know about astronomy. They're all amateur astronomers, and they know this stuff, but they maybe don't know this stuff. Anyway, let me show you this some more simulations in this one that was cute. Tesla Roadster in space, okay? So you can see that it's beyond the orbit of Mars. It didn't just go to Mars. It went beyond Mars. So almost all the way to Jupiter. This is in 2029. There will be a asteroid that comes very close to the Earth. There it is. You see it? 2029.
Oh, boy.
That's going to miss us in 2029, but that close. Okay, and that's a nasty one.
How close?
It will come in so close that it will come underneath the communication satellites that are stationary above the Earth.
Oh my! So that it's going to be where the satellites are. Where
Below the high stationary
so
satellites.
it will be visible then.
Oh, yeah, it might be visible.
How
Right.
big is it?
Let's see. It says it here. It says it has a 1 in 37 chance of hitting the Earth. Okay. How big is it? If it would release energy equivalent to more than 1 billion tons of TNT exploding, but it's not going to hit. That doesn't mean that it won't come back and try us again a few years later,
yeah.
because it's on an orbit which intersects the Earth every few decades. So they've looked forward a couple of decades, but they have to keep. This is definitely one they have to keep a watch on. Okay. So I want to see if there's anything else in the Universe Sandbox that I want to play with before I leave. Well, this is a good one. This is, we have lots of exoplanets now, thousands of exoplanets. In terms of exoplanets, there's no exoplanet that is really anywhere near the top of my list of fantasy favorites. There's no exoplanet that is near a star like our own sun, that travels around in a year, that has an Earth-like mass, that even has an Earth-like moon. There's nothing remotely like our planet in the thousands and thousands of exoplanets they've discovered before already. This solar system, however, tells a nice tale. This solar system tells a nice tale because it makes a good fantasy. The green zone is the area where it's considered habitable. So let's look. There are 3 planets, 1, 2, 3 planets in the habitable zone of this star called TRAPPIST-1. And the fantasy is, if there is life on these planets, there could be life on all 3. And maybe life developed independently on all 3. Or maybe there are space traveling civilization which travels between these 3 planets. There's no other planet system that we've discovered which is hospitable to life, it seems, as these 3. Of course, there is something wrong with this story, unfortunately. What's wrong with it is that this star is a very small star. And therefore, these guys are traveling around very rapidly, not in years, but in days. And this star, because it's a small stars have a very nasty habit of blowing up all the time. Not like exploding, just setting off giant flares. The kind that if our sun did it once every few hundred years would set back civilization decades, if not millennia.
It would fry us.
It would fry us, or just our instruments. Or maybe it would give us an enormous suntan. So these guys are sitting around the sun that you wouldn't want to go to in the first place.
How far away is this solar system? How many light years?
40 light years,
40 light years.
right? It's also, nice thing about it is it's within, it's local. We could go visit it. You know what I mean? I mean, not if we can visit the nearest star, which is 4 light years away. If you can fantasize that, this is only 10 times further. You know?
Nearly 10 times further.
Right. So you know you could go there. So this is one of the best solar systems. But I have to tell you, there is not even a good solar system out there. There's not a good one. But this is one of the top contenders for people's votes. And it has 9 planets.
Is it in our galaxy or is it another
40,
galaxy?
40 light years away is just a pimple pop away. It's nothing.
But it's in our galaxy.
It's in our galaxy.
It's in our galaxy.
Right.
So we're not talking about Andromeda or something.
Right. No. Anything else I want to show you? Nah. Oh, this is cute. You know, this isn't real. This is a sandbox. So somebody took the moon and decided to bombard it with asteroids. This sandbox is very good at doing this sort of game. This is not real. The moon was bombarded in its past, so there's no reason not to bombard it right now. So in this simulation allows for collisions of bodies with bodies and blowing up like this. So there you have somebody, not a scientist, but somebody who could have been just a kid playing in his backyard, decided to blow up the moon. So there you have it. That's
So
what the sandbox is.
The moon is disintegrating.
No, actually not. It didn't.
It withstands that bombardment.
Yeah, so you'll even see this thing cool off after it's bombarded. This is like the moon was hit,
Right.
bombarded, like this, over a period of a few hundred of million years. I told you that story last week, some of you who were
So
here.
this is, you're accelerating the process.
It's accelerating the process. There you have the moon. This did happen to the moon. It didn't happen in 12 seconds. It happened in 12 million years, or probably 112 million years. But the moon did get that bombardment. That's why it looks the way it did, right? And for those of you who were here last week, you also know that I told you that that's how the Earth got the water. That it didn't have to begin with. It got the water from the comets that came down and graced us with their water, because we didn't have our own water when the Earth was formed. Okay, that's the universe sandbox. Let's see what else I can find. That was $25 for those of you who are writing your checks. But it's actually pretty inexpensive. Starry Nights, which I'm going to start now, is an app that I'm actually sharing with one of the guys in the class. He and I went in on it, as it were. So we went in it for I'm not sure of the $80 or the $150 version, but because Kurt went in with me, built an application. He has an Android application which does the universe on your Google Watch. So he has apps that you can buy that essentially look like it's a clock, but the clocks are made up of planets and the like. And so if you buy his app, you get some cute stuff which he figured out from Starry Nights, and that's nice stuff. The Starry Nights I love Starry Nights because it really does tell you what the sky looks like right now overhead. This is maybe not so, this is Albany, New York, but this is what the sky looks like. And as I move as I move time forward, the sky darkens. I will see the sky. That's the way the sky looks in Albany tonight. And right here is, well, I stopped it too soon. Okay, but over here, so we're not going to do this thing can do lots of stuff. But one of the things that it can do is it can do some special little tools that it can do. One of the things I like that it can do is a flyby of the moon. So this is some spaceship flying by the moon, and this would be like, I'm sorry about those things. This is what it's like to fly by the backside of the moon. That is Mari, Orion, Tully, and this is the backside of the moon. Oh, that's the front side, sorry. So that's a flyby of the moon.
It looks like too much light on the front.
Too much light? It's not dark on the backside of the moon. It's just, no. It's just the other side of the moon. It's not the dark side, it's the backside. I like this one. This is called libration. And you know, when you look at the moon in the sky, it looks like a moon like you normally see. But this is the way the moon can look over a period of time. You never see it do this because you'd have to be on speed vision. But the moon does this in the sky over a period of weeks and months and years. And so we don't see 50% of the moon. We see over 60% of the moon because it does this sort of thing. And this is the way the moon actually does look in the sky over
Now,
time.
what accounts for that shaking?
The moon comes closer and further away from the Earth.
So it's all the gravity, Earth
Right.
gravity.
Right. The moon moves around the Earth in an ellipse. You've heard tonight is going to be the biggest full moon ever.
Right.
Well, there you go. You're seeing the biggest, the smallest, and the ones in between. They're not that much different from one another. There is a little difference, right?
It's a little bit sugar.
So next time you heard it's the biggest full moon ever, ignore that, please. Yes.
What will be, they say there's going to be a red moon January 29th. What makes it red?
What happens is if the Earth comes in front of the sun, it will block the light to the moon. Except the Earth has an atmosphere. So the sunlight goes through the Earth's atmosphere, and the sunset light, the light of the, when you look at the sun at sunset, it's red. Well, that red is what actually is the red light that hits the moon. So the moon becomes red because all the sunsets in the world hit the moon at the same time. Makes it red. It's not that interesting. I don't even bother to look up. It's one of the only things you can do in New York City that makes any sense at all. I don't even do that. This is called the moon illusion, and you all know the moon looks bigger on the horizon. So this is giving you a sense of what that looks like as the moon is. But when I zoom in on it, I have this little thing here. See this? That's a circle exactly the size of the moon. So the moon is always the same size, more or less. But when it's low in the horizon, it looks, in fact, bigger. So they're trying to simulate that here. Okay, so that is some of the favorites that they do in Starry Night. I also want to do let's see, the Royal Nebula. Let's see what this looks like. Ah,
Oh my.
this is interesting. See the size of the moon. That's something out there that you can see that is the size of the moon, and you can see it every night during the winter. I will show you why. Because it's Orion's belt. I need to find constellations. Hold on. No, don't do that. No, don't do that. I want, yeah, there we go again. And now, constellation.
That's not very good.
And I don't want to do that either. Yeah. See, I shouldn't have started this without practice. See, I didn't practice all of this, and I always do practice. That's what you're suffering through. Okay, you're suffering through.
It's very pretty, so keep going.
Yeah. Well, okay. What you're seeing here. Okay, this is another thing that you know. I didn't intend to do this one, but it's exactly what's cool. You heard the 12 signs of the zodiac.
Yeah.
12 signs of the zodiac? There are 12 signs, you know, Cancer and Leo and Capricorn and Virgo. And well, what is this going? Well, the sun is moving through the sky through the 12 signs of the zodiac. That's why there are 12. It goes right through them. Of course, the ancients were really cool. They couldn't see the sun going through these things because it was daylight, right? It was daylight when they were going through this. Nevertheless, they knew that the sun just went through Cancer, went through Leo, went through Virgo. Daylight. They were able to figure out that 6 months from now, I can see Virgo in the sky. I know where the sun was 6 months ago. It was going through Virgo. So that's the 12 signs of the zodiac. There are lots more constellations, but those 12 are the ones that give you all the constellation names that you know of. So each one of these tools has its own really cool things to show you. Tullys Database. Okay, this is a database. We haven't talked about galaxies hardly ever in this class because, you know, they don't count that much because there's only trillions of them. This one, billions. But this is a database of galaxies. This is not stars. These are things that are billions, not billions, hundreds of millions of light years away. Every one of these dots is a galaxy containing billions of stars. And the reason it looks like it's a square is because the guy who did this work, his name is Tully, for reasons of his own, decided to only plumb the skies like a square. So anything that was outside of his square, he ignored. So Tullys Database is a square in the sky stretching hundreds of millions of years wide. These are all galaxies. And you can see that there's a place where you can't see right here. You can't see all the galaxies because there's a place where the galaxies are blocked from view, and that is where the Milky Way itself interferes, and the dust in the Milky Way interferes right there. Right there. Come on, come by. Yeah. So I just learned I can't stop this thing from going. Can I stop it like this? Yes. I can stop it like that. Yeah, okay. All right. Next on the list, so that's Tully. What else should I do? Uniview is interesting because Uniview has the special ability to go from here, from the beginning of the universe to the end of the universe without me doing anything almost. So although it's very picky and it takes and you can't get it although you can't buy this, the one that they are building called Open Space will be for free and will be better than this. So this one is not as good as the one that is coming next. And it starts out, this is done by the Museum of Natural History and a Swedish company, and they charge for this. So I was given it, so you can't buy it. But it's designed for planetariums, so the planetarium can use the same software and project it on its planetarium dome. And in fact, the Museum of Natural History uses just this exact software to project. So you can see the Earth. You can come in and zoom on stuff. It's cool. I just messed up. Come back out. What I'm going to do, so you can zoom in and notice how the clouds came in and they went away. So it's also very cognizant of where you are. It lets you see different things. As I pull out, there's the orbit of the moon, there's the orbit of the planets, there's the sun, there's our solar system, there's the sun getting brighter and dimmer as we go away from it, there's the stars nearby. Oops, let me raise this bigger. And as I pull out even further, you can see the galaxy itself in the center of the galaxy. And I haven't done anything. I haven't done any manipulation, and believe me, there is a ton of manipulation that you can do. But all I've done, and I can, zoom around the galaxy and fool around with it. But I'm going to go further out. And as I go further out, suddenly, not before, but now, I'm seeing other galaxies. This is Tullys galaxies. These are Tullys galaxies. And they're colored, different colors, according to their associations with the ones nearby. So different colors only mean these are my friends, rather than this is anything special. So as we pull out even further, you see our Milky Way disappears. Those little green dots, those are our local galaxies. They belong to us. They orbit our own galaxy. They're our local group. I should wake. Oh yeah, we're at galaxies now. We're at galaxies.
Bravo, we got there.
We got galaxies. This is a particular galaxy cluster over here called the Virgo Cluster, and it is the nearest supercluster to our own galaxy.
How many light years away?
Probably 20,000 light years away, and
That's
no, I'm sorry, 20 million light years away. 20 million light
That
years.
image is stunning.
And yeah, so this is part of you. Uniview is really beautiful in terms of giving you a sense. This is galaxies. Every dot is a galaxy. And when I tell you that this is our local neighborhood, if the universe is very big, then this is our local shopping center. Okay? Although the universe is big, this is a teeny point of it. Watch as I pull out the Virgo cluster, which is red, will slowly disappear from your view, even though there are something like 2,000 galaxies in that red cluster. Okay? So you're seeing that you still see the red cluster. I wonder if we're going to see that square that Tully made. Okay, so now as we pull out further, other surveys are being brought into the story, and so Tully's data is now being merged with other people's data, the Sloan data, and other people who have done surveys, and that data is now being brought to the front. I'm rotating around this pile of now millions of galaxies. The Virgo cluster is still about there. You can see this, look at this. There's a band where there's no galaxies. Why are there no galaxies? Because the Milky Way is right here.
It's blocking it.
It's blocking the view.
Wow.
Right? So in answer to your question, how far can you see invisible light, which is not exactly the way you framed it, you can't see all of this because it's being blocked by the Milky Way itself. Yes?
Are all galaxies kind of flat, pancake-like, the way the Milky Way is?
Are all galaxies flat and pancake-like the way the Milky Way is? And that's a big no. Galaxies, literally, I've been teaching this course for like 12 years, right? 10, 11 years. One of the things that I've taught at one time was an entire class of the shapes of galaxies, because they have all these interesting shapes. But briefly, there are ellipticals. There are ellipticals that are very tightly wound. There are very loose ellipticals. There are ellipticals that look more like an egg, where the central bulge is gigantic and the rest of it is very flat. There are some galaxies that have no spiral arms whatsoever. And there are some galaxies that are just a mess, a complete mess, like they've been toyed with. And they have been toyed with by other galaxies. So galaxies, those would be irregular galaxies. And every one of those tells a story of how it was born and grew and now came to its adulthood at this particular time. Galaxies have stories because they hit each other. It takes millions of years for one galaxy to hit another galaxy, but that's okay. We got billions, of years to do it. So the galaxies hit each other with a frequency of every billion years. A galaxy hits another one. We're going to hit the nearest galaxy, nearest big one, the Andromeda Galaxy, in just a few million years. Our Milky Way and the Andromeda Galaxy, which is bigger than ours by a lot, Andromeda is going to come and swallow up the Milky Way for fun.
Is it sphere?
They're both spiral galaxies.
And so, are we rather lucky that if our Milky Way were, it could block our view of all of the universe if it were a different shape, right?
Yes. If we were in deep inside of a cloud, for example, we might miss the entire universe.
Because we're on the edge.
But we are on the edge, so we are blocked by only part of it. We could, if we were luckier, be above the Milky Way, because the Milky Way is very flat, and we lay in the pancake flatness of it. We could be above the pancake flatness of it. There's no rule that says you can't. Plenty of stars do that. We're just not among them. But if we were up there, we could actually see the galaxy looking down. The pictures we have of the galaxy that I've shown you are not our galaxy. They're just some other galaxy that we say, our galaxy probably looks like that one, so we'll use that one as a simulation for our galaxy. We've never seen our galaxy. We have an idea what it looks like. We don't know what it looks like. Yes?
Backtracking to something you mentioned before, the patterns of stars that someone named Gemini, Scorpio, Polaris, whatever those things are.
Pattern of stars and constellations, those names.
Right, and did you say that we see the same thing at the same time of the year each year?
We see the same constellation at the same time each year. 12 months, 12 zodiacal constellations, yes.
Is that, first of all, are they within our own galaxy?
They're within our own galaxy. They're within tens or hundreds of light years away.
Okay, then the next question. You said the sun is moving. Does that mean
The sun isn't actually moving. It's the Earth. You saw that sun moving through the sky. It was the Earth going around the sun. The sun was stationary. We were moving around the sun. So the sun was stationary in the picture. We were moving around the sun. The sun stayed stationary in the center screen. And as we moved around the sun, the stars behind it moved. So it looked like the sun was moving among the stars, but in fact, the sun was stationary and we were moving and the stars were moving behind the sun as we went.
But isn't the sun also moving?
The sun is moving, but that's irrelevant to this.
And we are moving with it.
Everything's moving, the sun is moving, but for the purposes of this discussion, the sun was deemed to be stationary. Since there's nothing in the universe that is stationary, you can at any given time assign the stationariness to any object, and then from that point on you can say what is going on related to that stationary point. Usually we assume the Earth was stationary, okay, not even spinning, for God's sakes. Then we said, well, it's spinning, but it still stays the center of the universe. But then, stationary. Then the Earth ended up going around the sun. The sun was stationary, but that didn't turn out to be true. There's nothing stationary. You just assign stationariness to an object. When Einstein came up with the theory of relativity, the word relativity on some level means relative to me, relative to you, relative to everything, because everything is relative to everyone else. That's why the relativity in the word theory of relativity. I'm going to just pull out a little bit more. So that, now look at that. That's a beautiful butterfly wing. Look at that. Look at that. Those are further galaxies, and now we're beginning to see. And by the way, the reason this now looks the way it is because the surveys are so expensive, they don't look at all the sky. Even though the Milky Way is blocking only some of the sky, their budget is only for some lesser piece of the sky. So what you're looking at here as we fly around is this yellow represents somebody's funding for that part of the sky. Okay? Right? So literally, you know, the universe is vast and we've seen a lot of it, but there's still more to check out. Statistically, we have enough information to do some very good astronomy, and if we looked at the rest of it, the payoff wouldn't be as heavy as having, you know, if you have data on 1 billion galaxies, the data on 2 billion galaxies is not going to be worth the funding necessarily. You know, so, and then as you pull out even further, you get more stuff. And these stuff are the stuff that galaxies are made of. This is, you've heard of quasars? Quasars are the most distant visible objects in the universe, and they are also the youngest, or depending on your point of view, the oldest. In the sense of they're far back in time, and because they're far back in time, they're also very early in their own formation. Our own Milky Way galaxy was at one time a quasar, but is no longer that. But these guys, being billions of light years away, are billions of years back in time. And they are lighting up the sky like crazy because they are literally forming the black holes that sit in the center of every one of those. And then pulling out even further, and look at all those quasars. See, I told you the Virgo cluster was meaningless when it came to the universe. Meaningless. All right? You pull out even further, and oops, what is this? This, no, there's a globe. I wish I could turn it a little brighter. There's a globe. You see the globe surrounding us? That's what they call the cosmic microwave background radiation. There's a sphere, 40 billion light years in radius, that is the signal from the Big Bang is coming from a sphere, 40 billion light years in radius, all around us, and I can't show it to you in this well because it's not dark enough. But I could darken it by fiddling for a bit. I'm not going to do that. So that's the universe, using UniView. And I just want to say that open space here, which is free, is supposedly going to do what I just did as well as I just did it without the pain of having to pay thousands of dollars for that thing that I don't, which was given to me as a gift. It should work as well. So, for those of you who, on January 30th, I have a class, but I'm going to be here next week, where I can tell you about where the class is. But that class costs money, right? Mm-hmm. How much did you have to pay?
It's a series of 6 classes, or $60, and you have to join the club, which is I think $35.
Right. So you're in for $95, and you get 6 other lectures, or 5 other lectures besides my own.
Yes.
Right.
Can I ask you a question, please?
Yes.
Do they have their own telescopes, or do you have to bring your own?
No, they don't do. So
They
far,
don't do that?
I didn't see anything with it. I only went to one class so far, just started.